All right, so today we're talking about algorithms. Let me just recap. Well, last week we went into heterogeneity and how important that is, and let's talk about a couple of things. So remember I talked about this CT to ED phantom, that curve of CT. So this is the phantom. Who's seen this phantom?
I had them at the RSNA.
They had them at RSNA. Okay, so this is it. I just wanted to show it to you. And each plug, these 1.0s, these are just water equivalent plugs. This is solid water. You can tell by the color that it's solid water. And then these are the density ratios right here. 1.05, 0.4. So this is probably some kind of lung. 0.4 is some kind of dense lung, and 0.8 is some not so dense lung. And then 0.9, this could be, I don't know, it could be polystyrene. 0.99, pretty close to water. So anyway, you put all those plugs in and you scan it, and then you look at this CT image. You put a region of interest around these plugs in your image, and it gives you the mean CT value. Okay, and then you plot that number versus that mean CT value, and that's how you get your CT to ED file. Okay. Do you know where to look for that in Eclipse? Where that file is? The CT to ED file. I'll show you when we go over there. Okay, I'll show you that too. Okay, so to correct it, not to correct, and I mentioned this quickly last class, but I just talked about it, so this slide has a little bit more information about it. European clinics have been correcting for many years for inhomogeneity, and most clinics in the US have been correcting for about 5 years. This is a little bit outdated. It's probably been more than 5 years now that most clinics have been correcting for inhomogeneity. Clinical patient data was based on homogeneous calculations. Okay, remember how I said that all the results from the treatments for lung, for example, came from homogeneous calculations. So all the results came from that. So it was a leap to start using inhomogeneity calculations. So there was lack of trust in these corrections and the algorithm. So that's why it took so long for us to move in that direction. Radiation therapy is moving towards greater accuracy in delivery and calculation with the advent of faster computers. Inhomogeneity is being adopted to improve those calculations, so it's also more accurate. Should be done cautiously due to the fact that we would be treating our patients a little differently from how we treated them in the past. Okay, so those are just some points that we talked about last class, and I just put them on a slide. All right, and then this is different examples. You know what? Can you hit the lights down because it's hard to see it? Thanks. It's hard to see the images. Okay, that's better. Wow. So these are just different examples that you guys will encounter in the clinic for artifacts, CT-based image artifacts. And why are artifacts important when we talk about inhomogeneity calculations? Why are we talking about them in the same?
So artifacts are going to affect the CT value of the pixels near them.
Right, yeah. So if we say, well, let's just calculate this with inhomogeneity, this is a humeral head, and this whole white area right here becomes a very high CT number. And look at this. This is black. I mean, that's not error. It's just black because when the X-ray tube came around, and this humeral head completely blocked any information that was on the side, and so that information is lost. There's actually the newer scanners, and we're getting some newer scanners at Evanston, Glenbrook, and Highland Park hospitals. They're coming in the next few months. They have metal reduction artifacts algorithms, and so they can actually restore this stuff somehow. Okay, so there is some information. They get this information from other views. Okay, so if they see something like that, I don't know how it really works. They gave us a talk, and I kept asking questions, and the physicist really didn't answer my questions. But what I got from the answers she gave me was that it doesn't use it uses other views to get the data about what's on this side of the humeral head, and so it really reduces that the shadowing effect. All right, so that's a humeral head. Over here, when we have metal dental work, you guys might have seen this already. So of course, metal in somebody's jaw, and dental work is going to also obscure. This is an example of an acetabulum, okay, a hip implant. Acetabulum and ball and socket joint. And then this is also something that we see sometimes that you got to be aware of. If the patient's too large for the scanner, and this typically occurs for diagnostic scanners mostly, not really radiation oncology scanners, because our radiation oncology scanner board is pretty big. Okay, so it doesn't occur, but it can still occur for patients really out there. But what happens is that if the field of view is smaller than the patient's body, you start to get these artifacts here. And again, that can cause that white area there is going to look like a really high CT number, and it's going to look like if you use heterogeneity, it's going to attenuate the beam more than it should. So you need to watch out for that. All right, so what do you do about those? So avoid CT-based heterogeneity calculations when artifacts exist in images. Okay, so once you have artifacts in the image, then you should say, well, we're not going to use CT-based, we're going to use contour-based or structure-based heterogeneity calculations. These situations require manual entry of organs. Okay, so in this case, with the metal implants, I think I already talked about this, but I didn't have the slides up. You assign the CT number of water to the whole body. Okay, so now the whole body's water, it's homogeneous phantom. And then you start contouring the areas that you think might affect your, or would affect your isodose lines. So CT number of air, you contour the air out, and you'd assign that a certain CT number. Okay, and then for metal, the same thing. You assign a CT number for metal.
I have a quick question.
Yeah.
From my experiences with it, actually that's a stupid question. When you take a contour and you say you assign it a CT value of 1, it usually grays out the entire thing.
Yeah.
The first question is, can you disable that effect for something like this, or would you have to assign the error first and then do the...
So when that happens, so the problem with the gray is that you can't see what's behind it, right?
Right.
The shadows it. So this is only an eclipse. Go to the left-hand panel where all your structures are and unclick it. Okay, so if you assign your body a CT number 1, which is the recommendation in this slide, this is all going to be gray. You're not going to see your CT information. So just unclick it. It goes away. Okay, but it still keeps it in the background. It's going to use it for calculation, but it's not displaying.
Question is, if you have an organ inside an organ, say,
oh, sorry about that.
Okay.
Yeah.
Say your tumor volume goes into your small bowel, but you imaged your bowel with
ovarian.
contrast.
Yeah, okay.
So you grade out your bowel.
Yeah.
And there's an overlap. Would the bowel CT number affect the target volumes?
Okay, so when you're planning this, you're going to contour your bowel, all that white area, right? And contour that and assign it 1. Right? Okay, so then your other structure is by default 1, isn't it?
Well, okay, so you have your tumor volume and your PTV, and your PTV extends into the small bowel.
Yeah.
Will it read that area as 1, or do you have to manually contour that bit of the...
Well, here, let me draw it. Let me just see. Just so again. So here's the PTV.
Right.
Okay, and you've got some bowel, I don't know, an intersection. Okay.
Right.
And this area was white because there was some barium on there. Okay. And then, but now you've assigned this a CT value of 1. Right?
Right.
Is that right?
Will
okay.
But
this is in this red area, this PTV, that's already 1.
That's already 1.
Yeah. So I mean, you've got 1 every, and now, but now it's not using the CT numbers to calculate heterogeneity.
Okay.
Yeah.
So that would be fine?
Well, actually, it could, because this area out here, the body, say this is the body, you haven't assigned that anything yet.
Right.
This you assign 1 by default because it's a PTV. This you assign 1. All these other CT values may not be 1.
Okay.
They'll be whatever they are.
Right.
Okay, and that's fine. Does that? So they'll be whatever they are, and that's okay. I mean, unless you've got more bowel out here that you want, that's white.
All right.
Yeah. So it'll consider everything that you assign. It'll consider whatever you assign it, and then everything outside of that, it'll be whatever CT number that is.
So even if you turn that structure off in all the calculations?
You mean off being display? If you turn off the display so you don't see it? Oh yeah, that just displays it so you can see it. The calculations are still whatever CT number you.
All right.
It's going to use whatever CT number you assign to it. Yeah. I know it's a little hard to understand what it's doing.
I only asked because this happened in clinic and I'm still not sure how we fixed it.
Oh yeah?
Yeah, we were getting weird dose distributions, and it was because the vowels which were assigned to CT of 1 weren't being seen as 1. So.
Well, actually, the Hounsfield unit is 0. That's the 1 and 0 are very close, but don't confuse your electron density ratio with your Hounsfield unit, because Hounsfield unit in Eclipse you assign Hounsfield units for densities, and in water is 0. Okay, not 1. XCO is 1, because XCO uses electron density ratios.
Okay.
Okay. So don't get those too confused. I mean, if you put 1 in Eclipse as a Helmsley unit, it's so close to 0, it's not going to make a difference. But just, you need to know the difference.
Right.
Okay. So in XCO, how would you do this in XCO? You don't assign CT numbers, again, you assign electron densities. Okay. What CT number would you assign for metal, though? What did you guys, have you done any of this in the clinic?
Yeah.
And I usually, for metal, I go in there with my CT number tool, because in Eclipse you can go in with a CT number, and I start like putting dots in there and getting samples of what the CT number is. And sometimes the CT number is like 10,000, it's crazy. So I usually don't go above 3,500. I just say 3,500 is my cutoff for a CT number, you know, because I don't know what it's going to do if I hit 10,000. I think it's going to over attenuate. I don't know.
Yeah.
You know? So I just stop at 3,500. That's my stop. That's just from experience, and it seems to work okay. Yeah. And then lung, make sure don't put minus 1,000 for lung, because lung does have some density. So also do a sample of CT numbers for lung if you have to assign lung. Okay, so now so all that heterogeneity talk was for photons. Now what about electrons? Electrons are dealt with in a very similar manner. It's pretty simple too, in terms of well, I shouldn't say it's simple, because there are simple ways of doing it and there are complicated ways of doing it. And just for our own heterogeneity calculations, when we're calculating monitor units and doses, there's a method here called the CET method, and this is in con. Electrons are affected by inhomogeneity more strongly than photons are, right? Because electrons they interact more readily than photons. We know that because they have mass and they have charge. So they interact with the material more readily. The coefficient, so the method we're going to use to calculate the heterogeneity is the coefficient of equivalent thickness. It can be used for calculating a dose beyond a uniform non-water medium. Okay. And scattering effects are not taken into account. It's a very simple, kind of like equivalent pathway. Right? So here's the formula. CET is the ratio, the definition of CET is the ratio of the medium's electron density, so the number of electrons per cc, to that of water. We've seen that already, right? That's the rho, rho over rho. So the effective depth is equal to the actual depth, the physical depth, minus Z times 1 minus CET. Okay, and this was the photon calculation that we had. Recall from photons d prime. So it's a very similar equation. It's not the same one, but it's similar. Okay. Okay, and Z is the thickness of an inhomogeneity. So d actual, Z is thickness of an inhomogeneity, and then CET is a density ratio. This effective depth is used to look up the PDD. So if you wanted to calculate the PDD at a certain point, you would calculate this effective depth to look up that PDD. It's a really simple equation. And then, so the CET values for a couple of materials are here. For bone, compact bone is 1.65, spongy bone is 1.1. So spongy bone is close to water, actually. It's only 10% higher in terms of electron density. CET for lung varies, and the average value is 0.5. And then see figure 14.24 for a graph of electron depth dose perturbation due to insertion of a quark. So let's do that. Do you have your book? Let's look at that figure. Where's our lights guy? And what's the number? 14.24. That might be the older version.
It's probably not the same numbers in mine.
It might not, unless I updated it. I've been trying to update the numbers to the newer version.
Oh, I think it is the same.
It is?
Depth distribution, water, and water quark transom.
Okay. It's either the same or I updated it. Okay. So that just shows how this just shows how it stretches out. How your PD, I don't know if you can see this, but I'll draw it here. So a typical, let's see, water core, depth of distribution of water. So they've got 18 MeV electrons, so this is PDD for 18 MeV electrons. This curve looks a little funny, but because there's no branch drawn in here. This is how they're drawing it. H2O phantom ion chamber results. Phantom. And then they have another curve. So this is and there's some quark in here. Okay, so there's quark up to a certain depth. So the red curve is with no correction, and then let's do it black. I'll just do a dotted blue curve. And then what happens when you put the quark? Well, your curve starts to look something like this. So it stretches out. Okay, which makes sense, right? There's a little bit more penetration when you consider the quark. Oh, and this is a depth dose calculation using the CET correction. Okay. All right, and then this is what an isodose distribution looks like. This is patient's skin. It's an axial cut of the patient's skin with isodose lines 95, 90, there's 80, 70, etc. And then over here you've got a lung. Okay. And I actually did this experiment with rando. You guys know who rando is? That anthropomorphic pen. It looks like a human. It's made of solid water. Well, it has real lungs in it. Well, real lungs. It has lung material in it. It has bones and vertebrae and everything, and sinuses. And it's a reproduction, pretty close reproduction of a human. And so I stacked film in there, and I irradiated it with electrons, and this is exactly what I saw. This is with no correction, and then once you correct it, the electrons look at how much more they penetrate. Look at the 10%. So that's something that you'll see in electrons, but not in photons. This huge drastic difference when you're in air. So electrons will penetrate a lot further than photons. Okay, and then the opposite is true for bone. I mean, if you had a piece of bone right here, this isn't usually too much of an issue, but many times we'll treat a patient, AP, and there'll be a node. This is a breast patient. There'll be a node near the sternum, and the node might be underneath the bone, and the doctor wants to use electrons. And I say, you know, that those electrons are not going to penetrate this bone very easily. So you need to keep in mind that the isodose lines that you're seeing here are not very accurate. You know, there aren't too many algorithms that calculate isodose lines very accurately for electrons. Eclipse, even Monte Carlo, they're not all that accurate. So when the doc wants to look at isodose lines for electrons, when there's air or bone, there's a big error bar in there. So I warn them about that. Okay, let's talk about algorithms now. Okay, so algorithms. There's a lot of stuff on the slide, but this is a summary of all the algorithms that you'll probably see. And then, so we're going to start with the most basic one, and the most basic one is measurement or correction-based algorithms. And those algorithms are, actually the only one that I can think of is the Clarkson integration. We've talked about that a little bit. And so how does that work? So it's semi-empirical, mostly based on measurements. Also called correction-based since they start with ideal conditions and correct for different conditions such as irregular surfaces. Okay, what does that mean? So these algorithms, they use all the data that you collect in your beam. So what data do we collect? PDD, profiles, alpha factors. They use that data to calculate isodose lines. Okay, so they take that data, and how do they do it? Well, how would you do it? If you've got some isodose curves, remember how we said we can plot isodose curves? If this is our tank, well, we can take our profiles and we can plot isodose curves like this. We could probably do this by hand if we had to. Okay. We can do that. And then we can take those isodose curves. In Excel, we can probably come up with a grid, an Excel spreadsheet, and each cell represents a dose, okay, in that grid. Okay, and then we take that grid, and then we say, well, now we're going to apply a beam coming from this side here, and we can add those two up in Excel and add one spreadsheet to the other spreadsheet, and we get a sum of doses. Okay, so that's how the Clarkson integration works. It takes the data that you've measured, profiles, puts them in an isodose shape on a grid, some kind of grid, and adds them up. Okay, that's all it does. And then what about a wedge? Okay, we don't take wedge profiles. So how does it handle a wedge? How do you think it handles a wedge? We actually did it in class. Well, first of all, the intensity through the central axis is reduced by the wedge factor.
Oh,
And we know that.
different.
Yeah, and then it looks at the source and it says, well, out here, this part right here is this thickness. It has, Clarkson needs to know the dimension of the wedge. Okay. And so it says, well, at this point here, I know that the thickness is whatever, 5 millimeters, and I know that the mu for that wedge is this, so it calculates the reduction in dose based on how we used it. Just e to the minus mu t. Okay, and that's how it calculates the reduction in dose. So it modifies these isodose lines for that. Okay, so that's when we say correction algorithm. That's one of the corrections. A wedge would be a correction. Another correction we'd see on these algorithms, the correction-based algorithms, would be a surface correction. So if this is the patient surface, the beam comes in like this. The fact that this is closer than this, it's going to correct for that. It's going to extend it SSD, and it does corrections for that as well. All right, so it starts with the simplest case, and then it corrects them. Okay. There's another thing it does too. Another correction, another example. There's several corrections that we're not going to go through them all, but there's several corrections. The other thing too is the profile that you enter will look like that. Now, what it does, it doesn't take all the data in this profile. It takes this central data, but then out here, these curves, it models these curves with a Gaussian type correction. Okay, so it says, well, the beam intensity in the middle is this, and it changes a little. Because of the horns, you remember the horns? So it uses that central data that you measured, but then the toe and the shoulder, it's going to model with a Gaussian type curve. Okay, so it does some modeling too. Now, how do you know how it's doing that modeling? Because, well, maybe after class we'll have a little time and I can show you. You actually put parameters in for the curvature of this and the curvature of that. And you play with those parameters until what the Clarkson calculates matches what you measured. Okay? All your measured data is, by the way, in the computer. It's there. You can look at it. Okay? And then it calculates, and then you play with the certain parameters until what you measured matches what it calculated. And in Clarkson, there aren't too many parameters to play with. There's just this, and you can look at them. You can look at isodose lines, and then of course you can double check your monitoring units to make sure everything's correct. The problem with this, and this is really fast calculation times because it's just adding numbers. It's just taking this one spreadsheet, it's adding it to another spreadsheet. It's just adding, and a little bit of modeling because of the shoulder. The problem with this algorithm is if you measure the data incorrectly, you have maybe one discontinuity, it's always going to show up in your isodoses. And it might be so subtle that you can't catch it. It might be obvious, it might be a big spike in your isodoses, but it might be subtle and you might not catch it. Okay, so that's the problem with this algorithm. The next type is model-based algorithms. Those are the ones that we're most familiar with, and the ones that you'll hear are convolution, superposition, and Eclipse AAA. The computer uses mathematical equation or models to fit its calculations to the measured data that you've taken. Now, all this requires you to take measured data. This measured data is used to adjust parameters to fit the model and match the measurement of all the fields and depths and accessories. Okay, so that's a model-based. The advantage here is that it doesn't need measured data. It's going to calculate the isodose lines and the profiles and PGDs based on its model, but you need to check it compared to you still need to check it compared to your measured data. Okay? And there is some user intervention that goes in there. But your measured data is not going to affect the model. And so if you mess up with your measured data and the model calculates it, you're going to say, wow, this model and my measured data look completely different. There's something wrong. There's something wrong either with the way I measure my data, or the parameters in the model. So so at that point, you do a sanity check and you can catch yourself. With this one, there's no sanity check, unless you're really careful. If you measure the data incorrectly, that's the data you're going to use to calculate your isodose lines. Monte Carlo is the third one, and Monte Carlo you've heard before, and that's based on random numbers and statistical physics and basic physics principles. It uses basic radiation physics like Compton effect, etc., to determine scattering angles and energies. It's the most accurate, but it has the longest calculation times. You can buy Monte Carlo algorithms today. Every manufacturer has them. For Eclipse, Monte Carlo Actually, Monte Carlo for photons, I don't think you can get Monte Carlo for photons, but you can get Monte Carlo for electrons in eclipse. And you can definitely get Monte Carlo for Axio. It's called Monaco. That's the name of the product, Monaco. And for Pinnacle, you use Pinnacle, right?
Yeah.
No, they have Peregrine. It's called Peregrine, the Pinnacle product. So anyway, they're all clinical these days. So in getting into a little more detail, Clarkson integration, 3D. So isodoses are based mostly on measured PDDs, OCRs, like I said, block and jaw transmission. Now, if you put a block, a cerebrin block in there, it needs to know how much is going through the block. And so you need to enter values such as half a layer of that block, the thickness of the block, etc. So those are some things you'll need to enter. All scatters calculated along ray lines emanating from the center of the field, ending at the edge of the field. Okay, and this was, remember the Clarkson integration, this is a beam's eye view, and you've got a block up here. Okay, and then it calculates, it starts at the center of the field, and it draws ray lines out, and it calculates a scatter based on that beam's eye view. That's how Clarkson works. Okay, so it just integrates around, it selects a starting point, and goes around theta, and integrates the scatter around there. And then it does this in a three-dimensional manner. And then everything's interpolated from measured data. So if the field size, if it calculates a field size of 14.5, but you never measured a PDD of 14.5, it interpolates between your 14 and your 15. Okay, so it's constantly interpolating stuff too. All right, garbage in, garbage out. I already said that. I should be treating correctly. Some mathematical fits are used. Okay, we talked about that. Toe and shoulders. 2D algorithm does not account for changes in patient surface. So it does account for changes in patient surface in one direction. So if this is an axial cut of the patient and the beam's coming in this way, it accounts for changes in left to right, but it doesn't account for changes in and out of the screen. Okay? So it just assumes that the whole thing is extruded like an extruded volume. So it's not as accurate as a true three-dimensional algorithm. Okay, model-based algorithms. So convolution superposition, most common, can calculate those points beyond the first interaction event site. And I'll have a drawing here in a second. I'll show you how that works. So it calculates, how does dose get deposited in a patient? You have let's pick a point of interest. There's a point of interest inside a patient. How does the dose get there? There's two ways. One is primary photons. They go straight to it. And then the other one is secondary. Secondary scatter. It's a photon that gets scattered. And the dose itself comes from electrons, really. Okay, that straggle over there. So, so the convolution has to be able to calculate the scatter dose as well as the primary dose. And Axio separates primary from scattered since they interact differently due to difference in energy. The convolution, this model-based algorithm, uses an energy spectrum to determine how many photons there are for each energy bin, an energy range. Now this is important because if we're going to talk about scatter, we're talking about Compton scatter, right? In Compton, the direction of the photon that gets scattered depends on the energy of the incident. Remember, h nu prime equals h nu naught. Well, the incident energy is going to affect the scattering angle. Okay, we know that. Okay, so that scattering angle is important for us. So we need to know what the spectrum of that beam is. We need to know the characteristic of that beam. So that's why we need to start with this with the spectrum of the beam. Longer calculation time than Clarkson, but more accurate, and it has full 3D capability. Okay, now let's look into a little more detail on how this works. The dose from a convolution algorithm is equal to the sum of the terma, the total energy released in the material, times the kernel. Okay, what's a kernel? All right, so a kernel, these are kernels. Okay, this screen right here. This comes from Con Figure 19.8. And let me just explain what this means. It's hard to see these because the type is so small. So let's see if we can figure this out. So the photon direction comes in this direction here, and this is a radial plot of the distribution. And what you're seeing here, and I'll point to these. See these red lines there? Those are isodose lines. Okay, isodose lines that are a result of a photon interacting with an electron getting some kinetic energy, and eventually depositing its kinetic energy in the form of dose in the patient. Okay, and then so that distribution is along these lines. So here's one right here. You see there's an isodose line here. There's another one here, another one here, and another one here. And this thing is just a little circle on it. That's just to show that it's a radial plot. But look, this is time sensitive -11, this is -10, this is -9, this is -8, and the units are down here. Units of centigrade per MeV per photon. Now this is cobalt-60. Okay, so per MeV, that means a monoenergetic beam. So it's per 1.25 MeV. But per photon, that's why those numbers are so small, because it's per photon, okay, for one photon. But it gives you an idea of how the dose is being distributed by a cobalt-60. So you see how there's very little backscatter here for this dose level, for 10 to the -8. There's very little backscatter. Now there's a little bit more backscatter, but the dose is dropping. Well, I mean there is some backscatter, but the dose is a lot lower down here for the same distance as it is down over here. So mostly forward scatter, which we know that. We know photons scatter in the forward direction. And then this is the depth, okay, down here. And this is, I think that should be centimeters. Now, so this is primary photons right here. And then what about first scatter? So this is first scatter. Now the first scatter, because the energy is lower, it's going to deposit less, it's going to create electrons of lower energy, therefore it's going to deposit less dose. Therefore these numbers are smaller, okay, 10 to the -12, 10 to the -13. Okay. And then down here is the sum of the two, the sum of this plus this. Okay, so that's primary per scatter. So those are kernels. That's what, when we're going to do the convolution equation, and we see the kernel, it's a two. Think of this. There's the sum. This is the sum. Yeah, that's the sum. Think of this two-dimensional description of a kernel. Okay, that's what that is. It's a matrix of values. Okay. Kernel is a small dose matrix that describes the relative energy deposited per unit volume as a function of scattering angle and energy. And kernels are generated from Monte Carlo. Now that is a cobalt-60 kernel. If I look at that's a 1.25 MeV kernel. If I look at a 2 MeV kernel, it's going to look different. How do you think it's going to look? Well, a 2 MeV kernel is probably going to deposit, this isodose line is probably going to be a little deeper, because it's got more energy, and so electrons can travel a little further. Okay. And it's also just, in terms of the energy depositing, it's depositing more energy because it carries more energy with it. Okay, and in a 4 MeV kernel, it's going to be even deeper. Okay, so each kernel kernels of different energies have different distributions. Okay, which means if we have a monoenergetic beam, we're going to need a lot of kernels. Right? We're going to need a kernel for every energy bin. Okay, and an energy bin is a little range of energies. If we're going to calculate this accurately, we can't just say, well, let's just average the energy. Let's just say, 6 MeV photons. Let's just say the average is 2 MeV. You can't really do that. You have to separate it into bins and treat them differently, because different energy bins have different quantities. And I'll show you that in a minute. And this is what an energy spectrum typically looks like. So calculation of polyenergetic dose kernels. To calculate the dose kernels, Monte Carlo code requires detailed information about the treatment beam spectrum. The energy spectrum is also calculated for Monte Carlo. So this is a spectrum, and this looks like PDB, but it's not PDB. So down at the x-axis energy in MeV, from 0 out to, if this is a 6 MeV beam, this would be a 6 MeV. This would be 6 MeV down here, and then this is 0 down here. Okay. And then log of relative number of photons. So this is quantity of photons. Typically, and this is a log scale, so it might look a little different. Typically, you have a lot of low energy photons on a 6 MeV beam, and then it just drops as the energy increases. And you don't have too many high energy photons, okay, in a beam like this. And this is not the energy that's in the patient. This is the This is the energy fluence that's coming from the head of the machine. Okay, this is the energy distribution. Okay, and why do you think there's a distribution? Why isn't there just one energy? So the electrons are created up in the accelerator, right? They're accelerated and they hit what? They hit a target. And then what happens when they hit the target? Yeah, Bremsstrahlung.
It's kind of, random interactions, so.
Yeah. The random interactions, and also, I mean, it depends. Remember with Bremsstrahlung, this was the nucleus, okay, and then here comes an electron. Electrons are red. Okay, and they curve around the nucleus, and depending how far they are from the nucleus, you're gonna get a higher amount of deceleration or a lower amount. If you're really close, it's going to pull it harder and it's going to give off a lot more X-rays than if you're further away, right? So that's what we get a spectrum. Okay, so that's what consists of. That's what describes this spectrum right here, the beam spectrum. So this is the energy spectrum of the beam that's about to impinge on the patient and treat the patient. Now, so how do we get that spectrum? Is it easy to measure a spectrum? It's not that easy. I mean, it's easy to measure quantity. We put a chamber in a radiation field, we can measure quantity. We measure Röntgen, we can measure sieverts, dose. But a spectrum is hard to measure. And there are spectrum analyzers out there. I don't know if in your undergrad labs, if you've ever used a spectrum analyzer where you put a source on it, and there's like a scintillation detector, and it can detect, and it can actually detect how many photons of a certain energy range, and then it shows you your spectrum. So there's spectrum analyzers out there, but we don't typically use those in radiation therapy. In radiation therapy, we use Monte Carlo code to calculate our spectrum. Okay, and the Monte Carlo code, it considers the energy of the electron as it hits a target. It considers the target composition. It considers the flattening filter composition. 85% of the beam comes just from the target and the flattening filter. The other 15% comes from scattering off the jobs and what's happening in the head. So all those interactions make up the energy spectrum of your beam. So these spectra, these are screenshots from Axial, by the way. Okay. And this is part of the beam commissioning process that we do. We start with the beam spectra, and then you see these little points. Those are all points that we can take the mouse to and move the points up and down. And this is energy and relative number of photons. So let's look at this. This is a 10 MV beam. So for 10 MV beam, it's a log scale again. Most of the photons are around 2 MeV. The majority of the photons. Very little photons are 10 MeV photons that treat the patient. So this spectrum, if I start playing with this and I make this spectrum look like this spectrum, because I can take this and I can say to XCO, okay, now calculate a PDD. Give me a 10 by 10 PDD and show me what the PDD looks like. And it's going to calculate a 10 by 10 PDD. And then I say, okay, now I'm going to change the spectrum to make it look like that. And the PDD is going to look completely different. Okay? And so because the amount of high energy and low energy photon contributions are different, and obviously it's going to affect the PDD, right? I mean, if I take this end right here, and I make these all straight, so we have a lot of 10 MeV photons, what's that going to do to my PDD? It's going to make my PDD, I can give you an example here. So here's a PDD, okay, with 10 MeV beam, and now I'm going to take these, I'm going to take this and I'm going to straighten this out. Straighten this out. Now my PDD is going to look like, what do you think why don't you tell me what it's going to look like? This is depth, and this is PDD. So if I take these high energy photons and I make more of them, and I now say there's a lot more of those, how is that going to affect my PDD?
The peak's going to be deeper.
This peak?
Stretch it out.
Just the high energy ones.
It's going to move towards the left, right.
It's going to move towards the right. I'm not touching these though. So the PDD curve, this area right here, is mostly, this shallow depths are mostly affected by the low energy photons. Okay, the deeper depths are affected by the high energy photons. So now I've just increased the number of high energy photons, so it's going to do this. It's probably not going to touch this stuff too much, but it's going to increase how much I can penetrate with that beam. Okay, so this is the modeling process that we do with Exio. We have measured data, and then we calculate what the model gives us, and then we compare. And then we start and we play with the spectrum until the model calculates what we measured, and it looks the same. Okay, so anyway, going back to these, this is a, just so you know, this is a 10 MV, 18 MV, and then this is a 6, looks like a 6 MV. Yeah, 6 MV. Energy, this is from Lutheran. They're all from Lutheran. And this is an early one. See how it's all choppy? It's an early one, where this is one of the earliest Monte Carlo spectra. And they use Monte Carlo because it's really the only way of calculating it right now. Okay, and this is the starting point. And then once you do the calculation, you compare your PDDs, and you play around it until they match. And you can get a really, really good agreement. Okay. And then why are you seeing two curves? One of them is the primary photon curve, and the other one's a scattered curve. Usually the one at the higher energies, the one that's lower, is the scattered curve. So this is scattered. Okay, and this is primary. Primary penetrates a little deeper because there's no scatter. Okay? Let's see, -1. And then comparing this one to this one, you have to look at the scale. So 1 times 10 to the -1 is here, 1 times 10 to the minus here. There's a lot more photons up in here for the 18. Okay, and if we have time, I'll show you that on Exio. Okay, now, so convolution, we're going to talk about convolution. There's have you guys heard of Salman Khan Academy online? It's this guy who just went crazy, and he just teaches everything. He's learned about everything. He's a very smart guy, and he's learned about all kinds of subjects. And if you go into the Khan Academy online, it's free education. It's pretty basic. It's not really high-level physics and high-level math. It's pretty basic, but he has a nice little refresher on convolution. Okay, that I sat and I watched, and it was really well explained. So I recommend you go in there. It takes, I think it's about a 10-15 minute talk. Okay, and then also if you want to plot stuff, there's a neat plotting website called fooplot.com. You can plot all kinds of stuff. So anyway, I recommend you look at that. So convolution, what is convolution? Who's taken convolution here in undergrad? You've done convolution? Okay. What kind, just analytical or?
We did it in electrical engineering.
Okay, so you understand the concept and how it works. So was that a signal processing class? A signal class or just a general?
We did it for resonant circuits.
Okay. Okay, how about you guys? You've done any convolution?
I guess I did. It is covered by a course called signaling system.
Usually it's in signal processing, yeah. Okay. So anyway, just a quick refresher on what convolution is. Convolution is taking two curves. It's an operation. You're taking two, and you're operating not on scalars, you're operating on vectors. Okay, so vectors, or you're operating on functions. You're taking two functions, and you're multiplying them together, and then you're integrating what you're multiplying. Okay, and at the same time, you're doing this over many times as you pass one curve over the other curve. Okay, so it's like blending one curve. Think of it as blending one curve into another curve. All right, so let's look at this graphically. Here's one curve f of x up here, and it's a little noisy. Yeah, it's a little noisy. There's a little bit of noise in the curve. Okay, then we're going to take this curve and we're going to blend this g of x into f of x. Okay, now we're going to call f of x f of u. We're changing we're changing the parameter because we're going to change, because this g of x is now going to become g of x minus u. Now, as u changes, this g of x changes position relative to f of x. Okay, so that's why we're putting that in there, because we want a parameter that's going to allow us to pass this curve over the other curve. Okay, so let's look at this third slide right here. What is this third slide? This third slide is the multiplication of g x minus u. Now, if we didn't have x minus u, and it was just g of x, then the g would just be in the center of it. Okay, so the g x minus u allows us to offset it. Okay, so now we're going to take g of x minus u, and u could be, I don't know, u at this point right now, u is this value right here. Okay, so u could be 5, whatever it is. So x minus 5. So that offsets the G curve. And what you're doing is you're multiplying the two curves together. Okay? So you're taking every value here, this value times that value, you're putting it here. This value times that value, you're putting it there. And you're going across and you're multiplying these two values and you're plotting it there. You've got a new curve now. Okay? So you've got a new function, the function of fu times gx minus u. So that's a new curve that you've created, and it's smaller. And it makes sense that it's smaller than this one because at this point here, the f of u is lower than g of u, so it attenuates it. Okay? It's a little lower. Okay, so now you've got a curve. What do you do with that curve? You integrate it. Okay, so you take the area of that curve. So the convolution is the integral of that multiplication. What happens when you integrate a curve? Do you get a scalar or a vector or a new curve? What do you get?
You get an area.
You get an area, which is a scalar. It's one number. If it's a definite integral, say it's a definite integral. Okay, you get one number. Okay, and so that number is that value on this new curve. Okay. Then you go back and you do it again. Now you're going to change your u. So this curve is now shifted this way just a little bit. You multiply them again and integrate it, and now you get another point right there. So as you're doing this, you're building this new curve. Okay, so why would you do something like this? What's the purpose of that?
Smooth the curve.
Right. You're smoothing the curve, exactly. You see how this was noisy up here? Because you just multiplied it by this curve that looks smooth, and you've smoothed your curve out. Okay. Now we've smoothed it quite a bit. I mean, we've almost deleted it. You know, it's almost flattened out. So the amount of curvature that this has is going to depend on how much you smooth this original curve. So if this function looks like this, it's not going to smooth it so much. Okay, it's not going to smooth it as much as this other curve. Okay, so a convolution is commonly used for smoothing, filtering, blurring. That's what it's used for. Is that what you guys, do you remember?
Yeah,
Yeah.
because like we'd have curves for like how a capacitor behaved and how
Yeah.
an inductor behaved, and then if you had them separately in the same circuit, it'd look all noisy.
Yeah.
And then we'd convolute them to see how the whole circuit would behave.
Convolve, yeah.
Yeah.
Uh-huh. Right.
It's like a sampling. Right? The U stands for sampling window width. I can't
For assembly?
that.
Something what?
There's certain points on the curve.
Uh-huh.
They make some like blocks. Can't remember exactly, but actually, and your resolution is limited by the frequency,
Mm-hmm.
the sampling frequency.
Mm-hmm. Yeah, we'll get into Fourier transforms too. And you can do all kinds of things. You can blur functions. Then you can, with signals, you can create filters. You can say, well, here's the signal. It's really noisy. I want to get rid of the noise. Then you use a low pass filter. Have you heard of a low pass filter?
Yeah.
That allows only low frequency to get through. Yeah. And this is where Fourier analysis comes in. Now, what that does is you're convolving your signal, the filter, and this filter in Fourier space looks like a low-pass filter would look like this. Low-pass filter might look something like this. Okay, and this is Fourier space. Now we're talking frequency. Okay, and this is intensity. So a low-pass filter would look like that. You're going to convolve this function with your signal, but it's only going to allow the low frequencies, and the high frequencies are attenuated. Okay, so. But this was distance space, and this is frequency space. Okay, it's different, and I'll talk about that in a second. Because what you can do with convolution is you can take this function and this function, take the Fourier transform. Now you're in frequency space. You're in a different space, and in frequency space, you don't have to integrate anything. You just multiply it. Okay. Then once you've multiplied it, then you take an inverse Fourier transform, and basically you've done a convolution. That's what a convolution is. Okay, and I'll talk about that in a second. I'm getting ahead of myself. But anyway, there's a lot of applications. So this would be a low pass filter, and then a high pass filter would be the opposite. A high pass filter might look something like that. You know, so you can do all kinds of great things with convolutions and and Fourier transforms. Okay, now how does this relate to dose? All right, a little mathematics side trip. Well, again, the convolution equation is what we're going to use to calculate dose, and this is how it works. This is a picture of a patient surface over here. The source of radiation is up here. Photons emanate from the source, come down, and then a photon interacts at a particular site and creates another scattered photon. Okay. Of course, there's a scattered electron, but we're not going to think of it the scattered electron because we're going to take it event by event, and we're going to assume that this event has scattered one time and deposited its dose right here. Then the other possibility is that the primary photon has emanated from the source and created an electron, and that electron has deposited dose here. So we've got a primary component and we have a scatter component. Okay, we always have those two components. We only think of the first scatter. The second scatter is not that important. There could be, at least in terms of explaining the theory, we'll just look at the first scatter. I'm not sure if there are other algorithms that look at second scatter and third scatter, but let's just look at the first scatter because that's what most of them are. And now, let's explain these vectors. This first primary vector is just it's the single vector. This is our prime. And then this, remember when you have two vectors to get the resultant, is just subtract one minus the other. And then, okay, so that explains this drawing. Now, the equation itself, how do we calculate dose from convolution? Here's the equation. Dose at point R, at this point right here, is equal to the integral. Now, this is over the whole volume. Okay, but this is a one-dimensional case just to keep it. Oh no, it's actually D3. It's over the whole volume. So, what is dose? Dose is equal to mu absorbed over rho, which we all know and love, times the energy fluence. Remember the energy fluence? That's the MeV per centimeter squared. Okay. At that point, at this point right here. So it's MeV per centimeter squared. Is the MeV per centimeter squared going to be the same here as it is here as it is here? They're all going to be different, okay? Because the amount of energy at a certain depth is going to be less than the amount of energy at the surface because of the attenuation. Okay, so this is going to change with depth. Is mu absorbed over rho going to change with depth? Only through beam hardening. Okay, and so this is a consideration. The regular convolution equation doesn't consider beam hardening, but the superposition does. Okay. So anyway, this is the regular one. So for the regular one, this is going to be constant. This is really what changes with depth. Okay, and then this is the kernel. Remember the kernel that we saw before? That's the little two-dimensional matrix that explains to us which way it's going to scatter, and how much of it scatters to the side, how much of it scatters forward, how much of it scatters backwards. This kernel is dependent on this vector right here, which makes sense because the kernel describes scatter, and this is your first scatter. Okay, we're going to integrate that over the whole volume. Now, this second line right here, all we did here is we just call this term. This is term. Energy fluence times mu over rho is term. Okay, and so that's the convolution we want to perform. Well, what's this? This could be our f of x from that previous slide. Okay, and then this is g of x. That's the blurring function. Why is the kernel a blurring function? Because if we didn't have a kernel and we just say, oh, let's just integrate the term, that's just going to give us attenuation as if nothing scatters. Everything goes straight. Okay, photon interacts with an electron and it goes straight. And then everything goes straight. And so we get this isodose distribution that would look like blocks. It would look like, basically, like our isodose distribution would look like this. Okay, and it doesn't. Okay, it's rounded, the corners are rounded. And so when you think of rounded, you think of blurring. So when we convolve this with this, our scattered kernel is going to round these out, and it's going to make shape the isodose distributions the way they should look, having considered scattering. Okay.
So why don't we use the three-dimensional kernel then? 'Cause it seems like if we're gonna,
The kernel is three-dimensional.
oh, it is.
Yeah. Mm-hmm. Yeah, it's three-dimensional. But you know, if you have to think of symmetry whenever you do mathematics, the kernel is circularly symmetric. Okay. So you can apply symmetry, and then you can say, well, the representation is a projection of this kernel, and you can represent it in 2D, like I had in that other slide. But you can assume circular symmetry for the kernels, which simplifies calculations. You can't assume circular symmetry for terma because it's going to use the patient's anatomy and the patient's surface, and that's completely random. Okay, and then this is just the Fourier transform. So why do I bring up the Fourier transform? Because to convolve this, and it's pretty hard to convolve this analytically. For computers, for humans, for anybody. It's very hard to convolve that analytically. So we're going to use a trick. First we're going to talk about Fourier transforms. You guys have probably heard, at least Laplace transforms. I think Laplace transforms, you cover it in undergrad. Fourier transform is just a mathematical relationship. The Fourier transform function of, and you know what, this slide is a little different than what I posted. Okay, I rearranged just a little bit. They're both correct, but I just rearranged this because it's this is a little more common, this form here. So, and there might have been a typo in the original one. So the Fourier transform, you'll see it as capital F of u, and u can be frequency. Okay? U can be units of frequency. That's typically what we see. Is the integral, infinite integral, indefinite integral rather, of f of x, some function, times e to the minus 2 pi I xu. Okay? And x is distance, and u can be frequency, and you're integrating that over x. Okay, so what it does, what a Fourier transform does, is it takes all the frequency components of the function f of x, and it calculates the intensity of those components. What does that mean? Why am I talking about frequencies now? Well, you can model any function. There's a little box down here that shows an example of this. Say I have a function which is the boxcar function. That's the function at the bottom. Boxcar function looks something like this. Okay. Where do you see this? Usually digital signals, right? In computers, you see boxcar function. So sorry. So what Fourier said that you can model any function as a series of sine waves and cosine waves, okay? Just by changing the frequencies of the waves and combining certain waves together, and you can model any function. So this is an example right here where he took a boxcar function and he modeled it with a whole bunch of sine functions. Okay, so you can take this function, add all these little sine functions, and then you'll end up with your boxcar function. Okay, so what is a sine function? A sine function can be very simply represented by a frequency. Okay, if you have a frequency, that's your sine function, one number. All right, so this main sine function has one frequency. Then look at another little one that has another frequency, another frequency, another frequency. So basically, you've just got a string of frequencies here. Okay, and so you can model this boxcar function with, I don't know, maybe 8 numbers, and not just 8 numbers, but the intensity for those numbers. The intensities are going to be different for those numbers. You see how these frequencies change in intensity? Okay, so you have an intensity and you have a frequency, and you can model any function with that. Okay. That is exactly what the Fourier transform does. Okay, it takes your boxcar function, say f of x is your boxcar function, you multiply it by this, integrate it, and then you end up with another graph. Here's your f of x over here, f of x. You're going to end up with another graph, which is going to look like this. Now, I don't know what the Fourier transform of a boxcar function is, but this is f of u. It's going to look something like that, like a string of frequencies with different intensities. Okay, so after I take my Fourier transform of my boxcar, that's the function I get. That's an example. I don't know if that's what it looks like. Okay. There's books of Fourier transforms. You can probably look it up and you'll find it in the book. And then, so now I've got this representation. Isn't that a simple representation? Now, this function over here is represented just by a bunch of lines. Now I can take this function and put it in here, and I can get my boxcar function back. So I can go back and forth, okay, between Fourier space and distance space. And the cool part is that in Fourier space, I can do all kinds of neat, simple mathematics, and then come back into distance space, where something that would be very difficult to do all in distance space, I can take the Fourier transform, just a simple mathematic, and then come back to distance space, and it just makes it a lot easier mathematically to do that. So it's a mathematical trick. And what do we usually do? Well, we're usually doing filtering. We're usually doing band pass filters, low pass filters. That's the kind of stuff we're doing in Fourier space. Okay, and see, notice that this one's the inverse Fourier transform is a little different. The negative sign's gone, and then you're also integrating over du instead of dx. Okay, so okay, now that's the Fourier transform. Again, it's hard to do an integral. Oh, the clock's gone. It's hard to do an integral with a computer, so we use an FFT. We use a fast Fourier transform, and that's an iterative approach. So in an FFT, this thing here becomes a summation from I to n, and then you just do an iterative approach. Okay, so this is the block diagram of how we're going to calculate dose. We take the fast Fourier transform of the terma and the kernel. These functions are now in Fourier space. Okay, so we take the FFT of, this is the terma. You know, we can say the, for example, as an example, the f of x can be the terma. Okay, and then we take, we do the same thing for the kernel. So we end up with two capital F's. And then in Fourier space, we multiply them. Multiply them together. Then we take the inverse Fourier transform of that multiplication, and that's how we get those. And then these are just some examples. Okay, so this is an example of a funny looking boxcar function. In Fourier space, it looks like a sinc. Have you heard of a sinc function? The sinc function is like a sine wave that you multiply a Gaussian to. Okay, and this is another. These are just some examples. Oh, there's a really good book by Bracewell, Ronald Bracewell, that explains all this, and it's called the Fourier Transform and its Applications, something like that. Okay, and then here's an example of a Fourier transform. Just going through the math. I took a picture of another example. Let's see. Give me a second here. Come on, Paul. So let f of x be e to the minus absolute value of x. Okay, and then the Fourier transform, there's your function multiplied by that. Okay, and then they go through the math. So there's some mathematical tricks that you need to be really comfortable with. I mean, because you can convert this into a cosine. There's a relationship or an identity between exponential, complex exponentials and trigonometric functions. So you can convert that into cos, and then they break out the real. Then they just say then you break out the real version of that, the real part of that, real component of it, and then you rearrange the arguments here. It looks like they also went. Looks like they went from minus infinity to 0 to infinity here by just changing it, by just using cos instead of cos and sine. And then it looks like they looked up the identity for this integral and put it down here, and they come up with this function at the end. And now the function is in terms of, see how it started in terms of x, and now it's in terms of s. Okay, s could be frequency again, could be anything. Oh, here's the identity. E to the ix is cos x plus I sine x. So I guess they just took the cos x and put it there. Oh yeah, that's what they did. And then they multiplied it by 2. Okay. So this is the function up here. This is e to the minus x absolute value, and there's the Fourier transform of it. Okay. And then these are just some more examples. And then whenever you take Fourier transforms, you're working with complex numbers. So at times you'll have only real, but at times you'll have only complex, and at times you'll have a complex and a real component of your curve. Did you guys take complex variables in undergrad? Complex numbers? So, you know what? Let's take a break. Yeah, let's stop. I can tell I need a break. My throat's getting dry. finish this up. Is it over here? Okay, so problems with the convolution. The integration equation can be done in Fourier space. Okay, we talked about that. So again, this is just a simple description of how we would do it in Fourier space. You take usually when you'll see a cursive f, that means that it's a Fourier transform. It's an operator. Okay, so this is pretend this is a cursive f. So this is the Fourier transform of the dose is equal to the Fourier transform of the terma times the Fourier transform of the kernel. Okay, so you take the Fourier transform of each one, multiply them, and you get the Fourier transform of the dose, and then you take the inverse Fourier transform to get the dose. Okay? And we talked about how that works. At this time, it's very time-consuming and very difficult to do. So we do an FFT. It can be used to decrease computation time, but it requires that the kernel A be spatially invariant. Okay, and what that means is that those kernels I was showing you on the screen before, they don't change with depth. They don't change with heterogeneity. They don't change with, well, basically the two main things are depth due to hardening and heterogeneity. We have to use this convolution equation, they have to be spatially invariant, so they're not going to change. And also it can't tilt, so the kernels may tilt in an interface between air and tissue. The kernel might look a little different because the scattering is going to look a little different. So that condition has to occur, that they're not going to change for this to work. Okay? Now, tissue inhomogeneity and beam hardening can tilt and change the kernel, so that's a problem. The X-ray treatment planning system, for example, uses FFT for homogeneous material and superposition for non-homogeneous. Okay, so we can satisfy this spatially invariance by saying we're only going to use convolution in homogeneous material, or when we consider the patient to be completely homogeneous, and then we're okay. And that works. The minute that we start using heterogeneity, we can't use the convolution anymore, okay? Because the kernel is going to change. The kernel is going to harden. It's going to, as you get deeper, that kernel is going to stretch out because it's going to harden, and there's going to be a higher component of high energy photons. So that's when we start using the superposition equation. The difference between the superposition equation and the convolution equation, you remember all those R's? Just put a rho in front of that R. What is rho? Is density. Okay. So you're just gonna modify that distance with density. Otherwise, it's the same. Okay, so how do you model this in XCO? And we'll go over this in a second. So modeling beam data with a fresh X-ray machine, you've taken your beam data, you transfer the data to your treatment planning computer, so you use your scanning system, transfer it to your treatment planning computer, PDDs, profiles, etc. Then model beam through spectrum adjustments and parameters. Okay, and the parameters are, oh, this is where I took a screen cap. The parameters, the spectrum adjustments we've already talked about. Those three spectra I had up on the screen, and how I can change that spectra to match my beam data. Okay, that's the first thing you do. The other thing you do is you model parameters. Let's see if I can read my screen here. I had a list of parameters that I got at the last minute. The parameters that you're going to model are going to be the size of your source. Yeah, do you ever take a picture and then you rotate it and you can't get it to?
My phone's too old to do that stuff.
Okay, so you're going to model the beam spectra, as I said. You're going to model the beam intensity variation across the field. Okay, so in other words, you're not going to model it, but it's going to use the convolution equation. The only part of the beam data that it uses, that you've measured, is the fluence. So different beams will have, the horns will look a little different. Okay, so it uses that initial fluence to model the beam. Okay, so it uses that, and then let's see, multiple collimators. Then it has to take into account multiple collimators, fixed wedges and compensators, dynamic wedges, and scatter outside the field, and then electron contamination. Those are just some basic parameters that it has to model. Okay, so once you've made all those parameters, once you've adjusted all those parameters, then it calculates the kernels. Okay, so again, the kernels depend. Remember how the kernels depend on energy? So it's only when we know when we're confident about our energy spectrum that we can calculate our kernels. Okay, then we create test plans and perform point dose measurements. Then we test everything, and then we plan actual patients, and we're done. Okay, so that's just the flow chart. Okay, Monte Carlo, named after a place with a famous casino due to random nature of calculus. That's where the name Monte Carlo comes from, because it's random, like a casino is. Okay. So what does Monte Carlo do? It follows the path of a photon from the target to the final dose deposition in the patient. So it looks at every possible interaction. It looks at the probabilities of each interaction. The algorithm uses probability distributions at every point it interacts. These result in angles and new energies with which the photon continues its journey. This is repeated until a sufficient number of photons have been emitted to produce realistic results. Okay, now the Monte Carlo algorithm is only as accurate as the number of photons that you use. The more photons you use, the more accurate it is. Slowest calculation times, but this is the gold. Monte Carlo is the gold standard. It became available clinically in 2007. Was invented before that, but calculation times were excessive. Okay, and some Monte Carlo codes that you'll hear is X4, Etran, ITS, MCMP is another one, Penelope, Peregrine, and there's a nice talk in the virtual library, 49th meeting. There are 2 talks on Monte Carlo by Charlie Ma and Dave Rogers. These are really good talks. I recommend these. So there's a whole bunch of talks in the APM website on the virtual library that you could just go there and watch it. Okay, and it's a really good way of learning stuff because these are people that are top in their field. And you just sit there and listen to it. Okay, so those are just look at those. Look at the 49th meeting and look at Charlie Ma and Dave Rogers' talk on Monte Carlo. Okay, and then so these are some comparisons on treatment planning computers and their accuracy. So we talked about Clarkson, we talked about AAA, Convolution, Superposition, and also Pinnacle has their own version of Convolution. It's called Collapse-Con. Okay. Now we're not looking at Clarkson. Clarkson is terrible compared to these. So we're just going to look at this graph here. This comes from a paper. Here's the reference down here, by the way, for this paper. Oh, this is my this guy Gino. He was my supervisor when I did my master's. Table 8, measured dose and dose calculated by analytical anisotropic algorithm. That's the Eclipse algorithm. In the CIRS, CIRS is a company that makes the phantoms. Actually, we were at the CRS booth at RSNet. They make phantoms. So they used the CIRS phantom at the Cross Cancer Center. And they looked at different energies here and different materials, tissue, bone, and lung. And this is what they measured at a certain point. It looks like this is at a certain point in the phantom. And this is what they measured. This is what AAA gave them, and there's the difference. Okay, measured dose and dose calculated by AAA. And then down here, table 7, doses measured with TLDs. In the next section of the this is the rando phantom at Tom Baker, also in Alberta, with Eclipse, AAA, and Pinnacle. So here they calculated AAA and Pinnacle. Here they just calculated measured versus AAA. Down here, they had TLDs at different locations. There's the measured dose from the TLD. Okay, and calculated dose by AAA, percent difference, calculated dose by Pinnacle, and percent difference. Which one do you think is better? Go down all the way to the bottom. Mean difference, 1.6 and 0.3. Okay, so Pinnacle does a little bit better. Maximum difference also does a bit better with maximum difference, and that's well known. And the reason is because Pinnacle uses a collapse cone, which is a convolution superposition algorithm. So Axial superposition and Pinnacle superposition are always going to outperform AAA. AAA is not superposition. Okay, this is another algorithm comparison. This is just a simple PDD of different algorithms calculating that PDD. So let's look at the worst case. Let's look at the best case first. The best case is gold standard, Monte Carlo. Okay, so gold standard is this one. That's your Monte Carlo. Now, what are we looking at? We're looking at a PDD going through water, and then at some point here we've got light lung. This area here is all light lung, and then we've got water again, or tissue. Okay, so tissue, lung, and tissue. Monte Carlo calculates the dose drops way down, okay, because lung doesn't absorb dose. So it drops way down, then comes back up when it hits tissue again. And then let's look at the worst case, this green ... green. So green ... that's the FFT Axio. That's the worst, that's one of the worst ones. And FFT, why is that bad? Remember what I said about the convolution and spatial invariance. When you have heterogeneity, convolution breaks down. Convolution algorithm breaks down. When you're a kernel, because your kernel changes slightly as your photons hit the surface. You've got a certain kernel, certain scattering properties, and that doesn't change much. It might stretch a little as it hardens, but once it hits lung, that kernel completely changes. It has to change. It has to stretch way out because now your photons penetrate a lot further. Okay, well, the FFT doesn't allow for the FFT algorithm only works with spatial invariance, with a common kernel, the one kernel. So that's why it's completely wrong, because it assumes a kernel doesn't change, but a kernel does change in lung. Okay, then let's look at this one, AAA. Okay, AAA. Okay, it's kind of in between. Not very good though. Look at the difference here. Okay, and here's collapsed cone. So this is collapsed cone. This is pinnacle. So collapsed cone. The blue one is coming pretty close to Monte Carlo, and I don't know what this pin is. Oh no, this is pinnacle. Collapsed cone. This TMS. This might be another treatment planning company that I'm not familiar with.
Maybe it's supposed to be CMS.
No, because CMS doesn't have a collapsed cone. So it's collapsed cone by somebody else. And then this is collapsed cone pinnacle. So collapsed cone pinnacle, really close. Now look at this, pretty good. A little offset there, but pretty good down here. What's this? This is superposition, MGS. Okay, Exio, a lot better. Okay, PBC is pencil beam, eclipse pencil beam, not very good. There's pencil beam. Okay. Pencil beam, here's that other company I don't know about, and they're not doing so well either. Okay, so take-home message, Monte Carlo is the gold standard, and then it looks like collapsed cone, pinnacle collapsed cone is pretty good, and Exio superposition is pretty good. Okay? All right, let's go.